Good day, everyone. My name is Damien Chippy, and today I'll be teaching you pure mathematics, CAPE Pure Maths, Unit 1. However, the topic I'd like to take on for today is one of the troublesome topic in Module 1, which is Principle of Mathematical Induction. Students always complain about this topic on the basis that they're not really getting the optics of how to go about dealing with principle of mathematical induction. I can understand in some way why. Number one, with this topic, you have to do a lot of explanation in regards to your moves, all right? And some students may have a bit of a problem because as far as they're concerned, this is maths. So why is it that we have to do all of this writing up and ensuring that, we explain ourselves when it is maths? But the truth is, students, maths, although it involves the core part is computation, but you have to learn how to express yourself. All right? For reason being, you want to give a reader a clear understanding of your computation. You get that? So, as much as I'm not the English teacher, however, I am more of a maths teacher, but the language is very much important as well. So, we're starting off here. So, this is CAPE Pure Maths. And we're doing Unit 1. However, under Unit 1, Module 1, but the topic that we'll be focusing is Principle of Mathematical Induction. Induction. Principle of mathematical induction. So, as I said, this topic, in my own experience teaching, this topic is where many students tend to have a problem with, an issue with. Even at my institution, I must tell you, I may have to do like a revision course on it or to ensure that I maintain some sort of understanding with the students. All right. Now, but if you follow me, students, I'm going to take you through the step-by-step process in dealing with principle of mathematical induction. All right. Now, also called PMI. So you hear, even in your exam, you understand me? You would have seen the author of the exam, which is CAPE, CSEC. They say PMI, which you would have understand the acronym is Principle of Mathematical Induction. So now, how we go about resolving Principle of Mathematical Induction, we take it on a 4-step process. Sometimes, depending on the text, they will take it to 5-step. All right? Now, step 1. First thing we do, we ensure that we have a defined statement, all right? So whatever the statement is, you are able to express the statement. So first thing is have a defined statement, all right? So have a defined statement, all right, where you say that the statement called the statement Pn is equal to a third n squared bracket 4n minus 3. All right? So you declare the statement. So mark it. This is just an example. So it's not really an actual question, but I'm giving you an example how you go about declaring your statement first. Now, step two, and again, students, don't worry about the declaration of your statement. Your statement is given in the exam, all right? So you just need to, in your whole process of going through it, you just simply need to declare or propose your statement. Now, the second thing you do is to because you want to prove in your students, what you're doing here is saying that I'm going to prove that no matter what value of n, considering that n is a natural number, and we all know that natural number start from 1, 2, 3, go on to infinity. You get that? Or if you want to say that n is a member of the positive integer, because the positive integer, students, remember integer is negative or positive whole numbers. So if I'm speaking about the positive integer, clearly what we're saying from here onwards, these are positive integer, which is natural number just the same. So you hear the examiner said, given that n is a natural number or n is a positive integer. All right? So, moving on. So first thing first, clearly, you know that the positive integer or the natural number start with 1. So after you have make a declaration of the statement, you then go on to say, okay, let n equal to 1. No. Simply, students. Now, what I want you to understand, what I want you to get, all right? The examiner said, let n equal to 1. What you're trying to prove here, in most cases, the statement going to have two sides, because you know equations have two sides, the left-hand side and the right-hand side, all right? Now, for you to prove that the statement is true for n equal 1, that is, when you substitute 1 on the left-hand side or the right-hand side of the equation, both sides will equate nonetheless. All right? So that's the first one. All right? So let n equal 1. And again, I don't need to write. Let me just tell you, this is to prove that whatever the statement is, we can rest assured that the left-hand side and the right-hand side will be equate. All right? Now, step 3. Step 3 here. Now, we then say, let n equal to k. Now, what is this? All right? Now, with this step, students, you must go on the assumption that the statement is true for k. Again, we don't know if it's going to work out to be correct or not, but when you reach this stage, you must just go on the assumption that n is equal to k. Now, after you have substituted the value of k into the statement, what are you going to do now in expressing yourself? I'm going to come to an example. Don't worry. I'm going to give you a clear, defined example of what you'll get in the exam. And I'm going to go through the step-by-step process. And you're going to see me right, because I'm going to do as I ask you guys to do in resolving the problem in the exam. So that one you don't have to worry about. When we come to let n equal k, what we're going to do, by the way, students, again, is to make an assumption that n is true. That is, we're saying that when we substitute n inside of the statement, we are going to know that we are going to assume that the statement is true for that value. Now, the Step 4, let n equal to k plus 1. Now this part now, students, out of all the steps, this part is what really gets students, they start pulling their hair, they start saying, what, how you get that, how you do that. To be honest, even reading the text at times, the students have great difficulty understanding, comprehending what is it that they're saying us to do. But I'm going to take you through a very layman. I'm a very simple man, so I'm going to take you through a very layman term of how you're going to get this. However, but let me just add that this step, at this step 4, when we want to let n equal k plus 1, what we're doing, student, is we have to have some form of knowledge of our quadratic equation, quadratic expression. Remember from CSEC, add maths, you're doing quadratic expression, student. Ax squared plus bx plus c. All right, we have to have an understanding of how we factorize this, because in most cases, step 4 represent manipulating the quadratic expression to get back to another side for you to prove whether the statement is true or not. And again, this is the area where students really have an issue with. All right, this, apart from the writing and explaining, this is the area where students really have an issue with. And then step five now, as I tell you, it depending on the text. Step 5, matter of conclusion. So these are 1, 2, 3, 4, 5 steps. Now you're doing pure maths. Now, yes, while it would be good for you to have some level of understanding with add maths, all is not lost for you nonetheless. If you are moving from CSEC maths to pure maths, you can still do the pure maths and pull through, which many students have before. All right, so all is not lost for you. All right, you just need your teacher to guide you properly and you're good to go. Now I'm going to do a perfect example, students, to take you through, because again, you're going to see me do a lot of writing. All right, you'll go wonder, wow, is this maths or is this something else? You understand me? But the writing, student, is just for me, you as a candidate, to actually express yourself. All right, so whoever the reader is, they have a clear understanding of what is done. All right, so let me get to that for you. Now, I'm going to erase all of here because, students, yeah, we're going to need this space. All right, you're going to realize that this whole board will be filled with just one question. All right, but don't worry about that. What you must do is to just focus on this procedure, the step-by-step approach that I take in order to solve the problem. Now, moving on. So, example 1 here. Now, we're going to prove that the inequality, prove that the equalities by mathematical induction is true for all values of n, for all values of n where n is a member of natural number, or you'll see the examiner use and the positive sign there to indicate that it's the positive integers. Remember, integers are positive or negative whole numbers inclusive of 0. However, the positive integers will cover the natural number section of it. So you have to be very keen now on this one, students. So here we have to prove that the equality of mathematical induction is true for all values of n. So now here is the problem. So 3r minus 2 equal to a half n, 3n minus 1. So because of this space, students, I may have to do them step by step, and so I'll finish with one step. I may erase the board. I may have to erase the board to do another step because sometimes the space is not enough, all right, based on the algorithm of solving the problem, all right? Now, remember step 1. We are going to define the statement. We are going to say, let the sum of r equal 1 go all the way to n, where the function on the right side is 3r minus 2 equal to the function on the left side, a half n bracket 3n minus 1. Now, so let this statement, let the function be the statement Pn. All right, so when I describe Pn, I don't have to write this every time I'm describing Pn, because Pn will now be the statement presented here. And what we're doing, student, we're proving that the left side is equal to the right side, given that for all values of n, given that n is a member of positive integers, or in other words, natural numbers. All right? Now, so this is the first step. Step 2 now, let the statement Pn, let the statement Pn be such that n is equal to 1. All right? So now, what will happen, student, is that, okay, we're saying that when n is 1, here on the right-hand side, when I substitute n on the right-hand side, here, whatever I get here, when I substitute n on the left-hand side here, it will be the same. Now you may be saying, but sir, over on the left-hand side is r. So, but you're still talking about n on the left-hand side. But here, student, remember here the summation statement state that r is equal to 1 to n. So that means n can be any value from 1 to whatever the maximum value of n is up here. You get that? So this r is also equal to n. All right? So although r is over here, don't confuse yourself that while we're speaking about n and at the same time r is over here. All right? Now, in most case, students, you take it on the right-hand side first. All right? Now, we have the right-hand side first. That's the right-hand side of the equation. Now, what we're going to say is substituting n for 1, a half times 1. And in the bracket here, we say 3 times n, which is 1, are we substituting, minus 1. Students, look carefully, So we're dealing with the right-hand side. In most cases, students, you're going to prove from the right-hand side, nonetheless. All right? So now we have a half times 1 is a half. Now in the bracket here, we have 3 times 1 is 3, minus 1, that is 2. However, a half times 2 is 1. Now, so this is the right-hand side. Now we're going to go on now to the left-hand side of it. Now, at the left-hand side, we have 3r minus 1. And again, do not concern yourself too much regarding that. Oh, sir, how you speaking about n equal 1? I must substitute it in here when it is r. We have here, again, from right here, we would have known that r is also equal to n. So here we have the 3r minus 2. So we have 3 times 1 minus 2, which 3 times 1 is 3, minus 2 is equal to 1. Now, after that, now students, we are going to now finish up our statement. Step 2, now finish it. We can then say, we can now say the statement Pn, the statement Pn is true for n equal 1. So that's the first proof, all right? Why? When we substitute 1 on the right-hand side, and we substitute 1 on the left-hand side, we see where both sides is equal to 1. Now, some of my students at my institution would then say, so sir, at all times, would it always be equal to 1? No, student, that wouldn't be maths. This is just simply saying that no matter what value is on the left-hand side, although you're going to get questions where most times them work it out, it's going to be 1, but don't limit yourself to that, please, all right? You're doing maths, pure maths at that, all right? So that means you'd have some level of understanding that equality means that whatever value is on one side, it's equal to the other side. So don't try to always skew your focus that it must be 1. It can be 2, it can be 3, it can be 4, it can be 100. It's just that if this side is 100, this side must be 100. That's all it's saying. Is that understood? That's how you prove that the statement is true for n equal 1. Now, moving on. So now if you notice, students, that I'm going to debunk many of your concerns. And I'm able to know your concerns because I normally get the question when I'm in the classroom. So don't feel surprised if I read your mind. All right? Good. Now I'm going to move on now to, I can write here, step 3. Now, step 3 is now called the assumption section, where we're going to assume that the statement is true for n equal k. And again, that's how you always state. State that once you're using n equal k, you must indicate that this is an assumption. An assumption means that you're saying that you think that this is true when n is equal to k. You're making the assumption that it's true. So now there's no clear working out that tell you that it's true at this point, but you're just making the assumption that n is equal to, the statement is true when n is equal to k. So we say, assume that the statement Pn is true for n equal to k. Now, again, take it from the right hand side here to make the assumption that n is equal to k. All right, clearly we can say we have got to the left hand side and substitute k right there. From all looks of it, it may not appear to be equal. Notice I said may not appear to be. Not that I'm saying that it's not equal. So you just, when you're doing the assumption statement, you don't worry about the left and the right side. You only take the right side, especially where you have the side where you have the function n. All right. Sometimes we have two sides, yes, and they have the function n. Take the right side nonetheless. All right. So now you're going to see when I read step 4, you're going to now appreciate what do I mean by taking the right side. All right. Now for step 3, we're going to substitute where the statement is true for n equal to k. So we say now a half k bracket 3k minus 1. Now it can be assumed that the statement Pn is true for n equal to k. So that is step 3. So step 1 here, step 2, continue with step 2, then we have step 3. So step 1 is the declaration, we're declaring the statement. Step 2, we want to prove that the statement is true for n equal 1. Step 3, we are making the assumption. We're not proving, we're just simply making the assumption that the statement is true for n equal to k. Now, I'm going to erase right here because we're now going to the part, and this is the problematic part. Students, I want you to look very keenly on what I'm doing. This part, I mean, if you notice, you might be saying from 1 to 3 first, okay, what's in that? Yeah, we're doing a lot of writing, but okay, fine, I understand. Now here is the tricky part. Now, moving on to step 4. Now at step 4, students, we are going to test the hypothesis. Now, it's an hypothesis, students, on the basis that you want to prove whether it is true or it is false. That's what hypothesis does. Hypothesis seeks to tell you whether whatever we have as the hypothesis is true or whatever we have of it is false. All right? Now, some of the questions students may ask, or you may ask, sir, would it always be true? Would it always be true? True to students, no. All right? However, you say, I'm in the habit of preparing you for your exam. Based on the level of questioning that CXC has been given the CAPE exam for over the years, they have not seen one. And I can tell you, student, I have been doing all of the type of questions over the different years. So I've not seen one where it was not true. And again, this is just the formation of your CAPE exam. In reality, nonetheless, student, of course, you're testing an hypothesis. Of course, sometime you're going to realize that your hypothesis is false in the real sense of the world. However, with regards to your exam, I've not seen, and I hope CXC hear me and tell, okay, let's just put in one where it's false. Okay? So, but I've not seen where they use one where it's false. All right, moving on. Now, so we're going to prove that the statement, we're going to test the hypothesis. So we're going to prove that the hypothesis is true or false when n is equal to k plus 1. Before I go into it, students, I'm just giving you the step-by-step approach in regards to this one, and I want you to look carefully. When proving the hypothesis, so step 1, so I don't want to say step 1 to confuse you, so I'm going to do it in bullets. First thing is that you're going to substitute n equal to k plus 1 on the right hand side. That's the first thing. All right? You're going to substitute n equal to k plus 1 on the right hand side. And you then simplify it down. All right? In many cases, you're going to get some form of a quadratic expression. All right? Or in its factor form. All right? Now, the next thing is that you then going to use the assumption statement, because this is very important to prove this. Use the assumption statement. Use the assumption statement to add to the left hand side, when n is equal to k plus 1. So in other words, here's the left hand side. You get that? I'm going to use the assumption statement pk plus 3r minus 2, given that n is equal to k plus 1. So that means what you'll have here is the assumption statement. Remember, this is the assumption statement, a half. And by the way, students, I'm just simply, before I go into it, because I know it can be confusing, I want to do this before I go through the whole thing. You're going to have a half, as we have there, a half k, bracket 3k minus 1, plus, we substitute n plus 1 inside here, bracket 3n plus 1 minus 2. And also let me use our rectangular bracket since we have a clear bracket inside. Now, when we do this, whatever this is, when we simplify it down, it must give me the right-hand side simplification expression. So therefore, the next part to it is that the left-hand side is equal to the right-hand side as an algebraic expression. So you'll clearly see it. So now I'm going to move on to that. Again, it will take your knowledge of understanding the whole factorization of the quadratic expression for you to able to manipulate the left-hand side in order to get the right-hand side. So now, here goes. Using the color code to indicate that this is me now going through the process of here. So we say n is equal to k plus 1. All right? N is equal to k plus 1. So we have the statement on the right-hand side. So here it is, a half bracket k plus 1, because this is a half times n. Rectangular bracket, 3 times n, which is k plus 1, close bracket, minus 1. Now, after that, students, we then simplify the expression, and it's best if you leave the expression in its factor form, all right? Now, you would have understand what I mean by factor form is where you have it like the quadratic expression factorized, and you have it in the bracket right there. So we have a half k plus 1 bracket. Students, we know that expanding, multiplying 3 by the k plus 1 here, 3k plus 3 minus 1, 3k plus 3 minus 1, we have 3k plus 2. So as it is now, students, on the right-hand side, the hypothesis is a half k plus 1 in a bracket and 3k plus 2 in another bracket. These are all factor in its factor form. Now, when you're doing this step now, students, now we're going to now move on now to using the assumption statement, which is the half k bracket 3k minus 1, to add to this side, all right? So now, the proof now. The proof, that's what we're interested in. Because the proof will line us back to this. We must get back the same expression in its factor form, all right? Now, so we say, using the left-hand side, don't forget it, students. So we're going to say whatever the assumption statement is, which is pk, plus the left-hand side, 3r minus 2. In other words, substituting r for n plus k. So sorry, not n plus k, k plus 1. But it's really n equal to k plus 1. So now the assumption statement right here, I deliberately did this because I know I'm going to need to get that information. This is the assumption statement from step 3. You would have remembered that the assumption statement is a half k bracket 3k minus 1. A half k bracket 3k minus 1 plus the 3r minus 2, substitute the r for k plus 1. 3r, so 3r, which is n plus 1, minus 2. So now it's a half bracket 3k minus 1. Follow me, student? So let us simplify this. This is 3 times n and 3 times 1. We know that is 3n plus 3 minus 2, which is then a half k bracket 3k minus 1 plus 3n plus 1. Now, from the look of it, as far as you're concerned, students, it's not the same. As far as you're concerned, from the look of it. All right? So, we are going to continue with this. Hold on, students. Here, let me remember, k plus 1, not, yes. So 3 times k, 3k plus 3 minus 2. Now would then give me 3k plus 1. Okay, moving on. So now we have, look carefully now, students. Let me go back to substituting n equal to k plus 1 on the right-hand side, which is k plus 1 right here, 3 times n, which is k plus 1 right here. Now, for the assumption statement, all right, the assumption statement would be a half k bracket 3k minus 1, which is right here. All right, so we had this plus this should give me the answer. So now, first thing first, I'm going to expand this times this, because if I should expand this out, student, I'm going to get a cubic. How do I know it's going to be a cubic? Because, it's not a cubic, we're going to get a quadratic. Now here goes, student, a half k times 3k is a 3 over 2 k square minus a half k plus, nothing to expand this by, 3k plus 1. Now, we know that in algebra, we add or subtract like terms. So this is 3 over 2 k squared minus a half plus 3 is positive, would have been now 2.5, which is 5 over 2 k plus 1. Now, if you get a calculator, students, you will see, again, a half k times 3k, a half times 3 is 3 over 2. You're doing pure math, students. We don't really rely on decimals. We tend to keep them as fraction, whether in its proper or improper form. 2, if it is that for any reason we're having surds, you don't simplify out the surd by putting in decimal, you leave it as a surd. You would have known what I'm speaking about. All right. Now, if the examiner wants you to put it as a decimal, the key word that the examiner will use is give your answer to 3 significant figure. Once the examiner tell you that, you know that a better than can do. And the answer must be given as a decimal, but then say, once you give it as a decimal, you're going to put it to 3 significant figure. But otherwise, students, work with your fraction, work with your surds without it being simplified. Moving on. Now, as you can see now, student, this is a quadratic equation where I'm going to factorize. Now, remember now, students, I want to factorize it in such a way that I get back the same thing here on the right-hand side. First thing first, students. Now, this is 3 over 2. This is 5 over 2. This is 1. If you notice that a half is already a factor, so I can factorize here for half. So if I have, using a red marker, right down here, I want to ensure that you're seeing it down here. All right? So that is a half. Now a half into 3 over 2, student, is 3k squared. Plus a half into 5 over 2 is 5k. Plus a half into 1. How much half you can get out of 1? 2, no sir? Good. So now we're then going to factorize here. Now take close attention because I'm going to erase over here to continue. I did say to you that this can take up some time on space, not time, but space. So now that I have a half bracket 3k squared plus 5k plus 2. Now, students, the examiner It's not expecting you to show how you work out the 3k squared plus 5k. You do it a little rough work because you already know what to do with regards to quadratic. So 3k squared plus 5k plus 2. We know that we deal with product and sum. Product A times C, the product is 6, the sum is 5. We know that, okay, 2 times 3 is 6, and 2 plus 3 is 5. So we have a suitable value right there. So we have a half bracket 3k squared. Again, students, you would have known how to do quadratic equation, more so factorizing the quadratic expression. So we have now plus, we have 3k plus 2k plus 2 right here. So this is now a half still. Now we are going to say, let me put this as a rectangular bracket. Now that we have 4 terms, we know that we take it to the groupings. Now I know that you would have known what I'm doing right here. Remember, this is not a CXC class. This is a pure maths class where this would have already been known. Had I was teaching a CXC class, and I give you the breakdown of this as you have never done it before. Moving on. Now, this is now, we say now this is 3k is the common factor. So this is k right here plus 1. And then plus 2 is the common factor right here. So 2 into 2k is k. 2 into 2 there is 1. So now we have a half bracket 3k plus 2 in a bracket and the k plus 1 in another bracket. So in other words, this is a half times 3k plus 2 and k plus 1. Now, if I look back to what I have here, you would have find that it's the same thing. Now, for those of you who are wondering, the k plus 1 is right here. Well, it doesn't matter. Again, 2 times 3 is 6. And then 3 times 2 is still 6. So it doesn't matter. Remember, multiplication is commutative. All right? And we all know that already. So now that we have proven the hypothesis to be true, you understand me? We can now go ahead now and declare that the statement is true for all positive integers. So now this is now my statement. So now we say since the left-hand side is equal to the right-hand side of the hypothesis, of n equal to k plus 1, remember, we now say the statement Pn. We now say the statement Pn is true for n equal to k plus 1. Now, the fifth part where we talk about the conclusion, we're now concluding that for whatever value of n, we can now say the statement is true. Therefore, the statement is true for all values of n where n is a member of integer, the positive integer, or n is a member of natural number. And that would be the answer. Now, students, I'm going to go through another one because I know for sure, I'm in my physical class, the students want to say, okay, sir, do it again. I want to see if your methodology work for another question. I can understand. So now we're going to do this again. So remember now, student, it has 5 steps. This is the conclusion, step 5. All right. Step 1 is where we declare the statement. Step 2 is where we prove that if n is equal to 1, the both side is still equivalent. Step 3 is where we make an assumption, just an assumption. However, step 4 is where we go ahead and prove an hypothesis, given that n is equal to k plus 1. All right? Again, and it's very important for step 4, the hypothesis. If you notice how I did the hypothesis, let me just go back again to show you. In proving the hypothesis, now watch again. In proving the hypothesis, first thing, we substitute n equal to k plus 1 on the left-hand side. That's 1. 2, we then take the assumption statement, pk, plus the right, this is put to the right-hand side. Good. Substitute n equal to k plus 1 on the right-hand side. Then we say the assumption statement plus the left-hand side being substituted for n equal to k plus 1 just the same. And what we're going to see is that the left-hand side must be equal to the right-hand side with regards to an algebraic expression in its factor form for the most case. All right. I think I had a student some time ago where she feel better expanding the bracket and simplifying. I tell her to continue to do so because, again, you're still proving that the left-hand side is equal to the right-hand side. Is the same thing you get, nonetheless. All right? But as I say to her, that would just be additional more work and time. That is our enemy. All right? So let me go again, students. Let me go again with another example. Let me go again with another example. Again, students, in Module 1 of the K Pure Maths Unit 1, this topic, mathematical induction, is one that is not so much loved. All right? Let me go again now. Example 2. Now here we have prove the equality by PMI, and we know PMI is principle of mathematical induction. The sum, given that r is equal to 1 to n, on the left-hand side. Now I'm going to go for something, a bit more challenging, so you understand where I'm getting at, all right? But don't be dismayed, students, with what I'm doing. If you notice, look at the optics. I'm following the algorithm. Once you're following the algorithm, students, no matter how complex or how simple it is equal to the same thing. All right? Moving on. Now, that is n plus 1. So this one is more compounded. It's more compounded, students. But if you watch it, you're going to see that I am going to follow the algorithm. I'm not going to do nothing differently than what I tell you how to go about it. So when I put this on the board, first thing you have to say to yourself, what is this? You understand me? However, students, and let me make sure we take down the question correctly, r square plus r cube. So one is cube, one is square. All right? So r square plus r cube is equal to n bracket n plus 1, open bracket again, 3n plus 1, n plus 2 over 12. All right? Now moving on. For all values of n is a member of natural number. This upside down A here, students, in mathematics is for all values of. You get that? For all values of n is a member of natural number, given that n is a member of natural number. Now, moving on. Again, students, watch. I'm going to first, step 1, declare the statement. Let Pn be the statement the sum of r equal to 1, given its n, bracket r squared plus r cube is equal to n bracket n plus 1, 3n plus 1, and n plus 2 over 12. So that is the first step we make with declaring the statement. So that means when we refer to Pn, going forward, we're referring to the statement here. All right? Now, step 2, we said let Pn be the statement when n equal to 1. Now remember, when n equal to 1, students, what you're doing, you're proving that whatever the value is on the the right-hand side, all right, so this is the right-hand side. Whatever the value is on the right-hand side is equal to whatever the value is on the left-hand side. Remember now, the students, you're proving the statement when n equal 1. So here goes. So we're going to deal with the right-hand side first. P1, as we know, it is 1 bracket, so substituting n for 1. So it's 1 plus 1 bracket 3 times 1 plus 1 bracket 1 plus 2, everything over 12. Let me see this. So this is 1 times 2, because this is 1 plus 1 is 2. 3 times 1 is 3, plus 1, that is 4. 1 plus 1, that is 3, over 12. We know that 1 times 2 is 2, times 4 is 8, times 3 is 24, over 12, which is equal to 2. So the right-hand side is 2. Now, students, remember, although I tell you that, many of the questions that you get when you put in n equal 1 is just that you're going to have 1 on both sides. However, I said to you that you can get another value. That's why I try to be deliberate in selecting my question, because I want you to understand and appreciate that as long as you prove that n equal, both sides are equal. Now, the next thing now, the left-hand side. On the left-hand side, which is right here, so we said 1 square plus 1 cube. 1 raised to any power is 1, plus 1 raised to any power here, 1, still equal to 2. You get that? So now we can say, hence, the statement Pn is true for n equal to 1, since the left-hand side is equal to the right-hand side of it. All right, so that is the first one. Again, student, this one will be more compounded, all right, as you can see. Moving on, next one. All right, you realize I did nothing different from what I did earlier. All right, so moving on, going to the assumption statement. So that's the first. Now, step 3 now, assume that the statement Pn is true for n equal to k. That's the assumption statement. So hence pk right here. Again, go out for the right-hand side. Students, go after the right-hand side with the assumption statement. We have k bracket, k plus 1 bracket, close bracket, open bracket, 3k plus 2, close bracket, open bracket, k plus 2 over 12. This is just the assumption statement. Then you write, it can be assumed that the statement is true for n equal to k. Student, did I do anything differently? I think not. All right, so let us continue. So this is the assumption statement. But I'm just going to put the assumption statement up here because I'm going to have a drawback for it, as you know. All right, so which is k bracket, k plus 1, 3k plus 1, and k plus 2 over 12. You don't have to draw back for that, that's all. Going on now to the fourth one. Now, so step 4. All right, let's see. I'm going to try to be, all right, for step 4, again, we're going to test the hypothesis. Test the hypothesis that the statement is true for n equal to k plus 1. We are now testing the hypothesis. All right? So, first thing, for the right-hand side of it, all right, pk plus 1, what we're going to do is substitute k plus 1 on the right-hand side. So this n here is k plus 1. Good. Here, this n here is k plus 1 plus 1. So n plus 1, this is it. Here, 3 times k plus 1 plus 1. So this is 3n plus 1. Everybody get that? Now, moving on to this now. This is k plus 1 plus 2, which is the n plus 2. Everything over 12. And of course, I'm going to simplify this, students. Simplify this. So this is going to be k plus 1 right here. Right here, nothing to expand this bracket by, so it's the 1 plus 1 is 2. So this is going to be k plus 2. Right here, we're going to multiply the 3 by the k plus 1 here. Would that be 3k plus 3? But the plus 1 right here would that be plus 3k plus 4. So here we have 3k plus 4. I hope you see how I deduce that, students. And then here now, nothing to expand this bracket by, so it'll be 1 plus 2 is 3. So this will be now k plus 3 over the 12. And can I say, students, this is easier than the one that I did earlier, although many of you, when I look at it and you run past this, because as far as you're concerned, this is, you're not going, You never attempt to try to have no brain surgery as far as you're concerned. And if you just go through the algorithm, you realize that this one is so easier. It makes it easier than the one that we did previously. So now, moving on. Moving on. No. So this is the the right hand side. Now we now move on now to the right hand side. The left hand side, sorry. Now, students, remember with the left hand side, this is the formula. Again, catch the optics. The assumption statement plus whatever is on the left hand side, r squared plus r cubed, close bracket, given that n is equal to k plus 1. So this will be k plus 1 square plus k plus 1 cube. Students, very, very important now that you understand that. So remember, this is the assumption statement, which is this. All right? Now, when we add it to the left-hand side, we should get back this. All right? Now, let's go. Just stay focused, students. That's all you have to do. So here goes. We have k bracket k plus 1, the assumption statement that we're dealing with, student. The assumption statement, 3k plus 1, and then we have k plus 2, everything over 12, plus here we have n plus 1, remember k plus 1, not n plus 1, k plus 1 square plus k plus 1 cube. So when we evaluate all of these, students, we should get back right here. Now, let us continue. Now, there's nothing to expand this bracket by. So we will remove the bracket, this big rectangular bracket, which is then now equal to k bracket k plus 1, 3k plus 1, and then we have k plus 2 over 12 plus here we have k plus 1 square plus k plus 1 cube. Now remember, your knowledge of factorization would be greatly appreciated. Now, if you look at this right here, students, look at this one right here. What is the commonality between, and again, between the pluses? What factor is the commonality? Here we have k plus 1 here, we have k plus 1 here, and we have k plus 1 here. Now, all we're going to do, student, is factorize for k plus 1. So we're going to factorize all of this right here for the common factor k plus 1. Watch it, student. Moving on. So k plus 1 would be the factor. So now k plus 1 into this, cancel out this k plus 1. So now all we have is k bracket 3k plus 1, close bracket, k plus 2 over 12. Plus this k plus 1 into k plus 1 square, students, is simply this, k plus 1 square over k plus 1. That cancel that, it give you the power, it give you the same base, but the power is now 1, k plus 1. So now, this into this is just simply k plus 1. Plus k plus 1 into k plus 1 cube is give me now k plus 1 square. And this is this so far. This come down to this so far. Now, all I'm going to do now, students, remember now, all I'm going to do, we have a 12 right here. So what I'm going to do is take the denominator 12, which become 1 over 2, 112. So now we're going to put So we have 112, bracket the first factor, k plus 1. Now what I'm doing, student, is removing the 12 here so we can easily deduce a quadratic. That's all I'm doing, students, all right? So now, moving on. So we have 112 into this is all of the numerator right here, which is k, bracket 3k plus 1, open bracket, k plus 2. Now, 112 into this, give me now plus 12 bracket k plus 1. 112 into this, give me now plus 12 bracket k plus 2 square. Because I don't want the denominator involved. All right? So now, we have, sorry, k plus 1, not k plus 2. Good. Now, moving on. Now, after we have this now, students, we have k bracket 3k plus 1, close bracket 3k plus 2, and all of that. We are going to now expand and simplify because we want to get everything in one where we can factorize it. So now, moving on. So now, here, we're going to have 1 over 12. We're going to have bracket k plus 1. Then right inside here, we're going to have 3k times, we're expanding this, by the way, students. Let me see if I can factorize without expanding, or let me see if I can. This is 12k. If I can just expand, I'm going to expand right here, students. Rather than expanding here, I'm going to expand right here. And then I'm going to factorize for another, either k plus 1 or k plus 3. Watch and see. So we're going to have k bracket here, 3k plus 1, k plus 2, plus, expand this bracket is 12k plus 12, plus, we know that k plus 1 square, students, remember k plus 1 square, using perfect square method, is k squared plus 2k plus 1, all right, times 12, because remember the 12 is beside it, is now 12k squared plus 24k plus 12. Simplify. So 112, k plus 1. So we have k bracket 3k plus 1, k plus 2. Now, student, this is where many of you falter, not because it's not possible, it's because the process of computation, that's what you guys have a problem with. So now, like terms, so we have 12k plus 24k, so we have a 12k square plus 12k square plus the 24k plus the 12 is 36k, and then we have 12 plus 12 is 24. Now, students, I'm going to now need up here now I'm just going to do a rough work to show you how I'm going to factorize this right here. 12k squared plus 36k plus 24 plus 24. Now, if you realize, students, is that what is common between 12, 36, and 24 is 12. All right, so this will be k plus 3k plus 2. Because, again, I simplify it down, students, so as to have a smaller number to work with. Then I'm going to factorize this. We know the product is 2, the sum is 3, so it's 1 times 2. So it's k squared plus k plus 2k plus 2. So now all of this here would give me k bracket k plus 1 plus 2 bracket k plus 1. So it's k plus 2, k plus 1. So all of this right here, students, let me, you know what? This, I'm going to put this up here because I need my space. I'm going to put this up here. So now I get a half, not a half, 112 k plus 1 bracket. K bracket 3k plus 1. 3k plus 1. Remember, students, I'm trying to see 3k plus 1, k plus 2, plus I have I'd factorize out right here. So which is now equal to k plus 2, k plus 1. K plus 2, k plus 1. So I can take this off here. Now that I have this right here, students, now that I have that right there, if you notice what is common between the plus is k plus 2, k plus 2. So again, I'm going to put the k plus 2 outside here now with this to then take out the to factorize out the k plus 2. So now it's 1 over 12 bracket k plus 1, k plus 2. So now remember, now it's this k plus 2 now we're factorizing out. K plus 2 into this, cancel it out, leave it back with k bracket 3k plus 1. K plus 2 into this just give me plus k plus 1. So now when I expand this and factorize it out now, student, so just doing the rough work here, because that is not really needed. So I'm going to expand this and factorize it out. So we have k times 3k plus 1 is 3k squared plus k. Then we have plus k plus 1. Add or subtract like terms, 3k squared plus 2k plus 1. Then we're going to factorize. Product is 3, sum is 2. Product is 3, and the sum is 2. So now 1 times 3. No, so we're not going to get that. So here, we are here now. So this is, when we expand this out, we get 3k squared plus k plus 1. So that is now 3k squared plus 2k plus 1, which is this. All right? So now, moving on. So for our students, if you notice this, we have the k plus 1, we have the k plus 2, and we have the 112. This here is us saying this is 112. All right, so the next one that we are going for now, we should have 3k plus 4, k plus 3. All right, so that will be the next factor. But let me check my computation, because if this is the product, so this is 12k squared plus, okay, 12k squared plus that. We had, this is it right here, and we had the 12. So this was the 12 into that. Good. Because we divide all of this by 12. All of this by 12. So we have 12k. So it's really 12k plus 12. So right here now, I should have, right here should have been 12 bracket k plus 1. No, okay. So now, good. So the same 12. So now this is k, 3k squared plus k plus k plus 12k plus 12. So now it is now 3k squared plus 13k plus 12. Again, we're going to factorize this. Product is 312 is 36, and the sum is 13. So the two numbers, when you multiply to get 36, when you add it to get 13, so that will be 2 times 18, no, 3 times 12 is 36. We have 4 times what is 36? 4 times 9. 4 and 9. So we have 3k squared plus 4k plus 9k plus 12. Factorize this out. For here we have k. So this is now 3k plus 4 plus 3 is the common factor right here. 3 into 9k is 3k and plus 4. So now it's k plus 3, 3k plus 4. So now all of this now, students, is now equal to 1 over 12 bracket k plus 1 bracket k plus 2 bracket k plus 3 and open bracket again 3k plus 4. And look at this and this, students. All right, we can see that we have all of these factors. Now your next question that you're asking about is, sir, how you have 112 here and you have 12 here? Students, remember, if I have a fraction times another times that value, says times b. Put this over 1, it will be b over 12, just the same. So when all of this is times by 112, it is now the same thing as k plus 1, k plus 2, k plus 3, and 3k plus 4, all divided by 12. And that would be the same thing. So even though you may say the order of the factor, it doesn't matter the order of the factor, it's the same thing right there. All right? And then we could simply say that the statement is true for n equal to k plus 1. You have proven the hypothesis. On the basis that you have proven the hypothesis, you can then easily state that the statement is true for all values of n equal to n is a member of natural numbers. Now, so this one was a heavy one, all right? This one was a heavy one. So now, again, students, let me do a recap now regarding to prove the mathematical induction. Again, students, you're doing pure maths, your computation skills. You must have your computation skills. So all you need to do, once you have your computation skills, all you need to do is then worry about, okay, my procedures, the algorithm in solving the problem. Again, just recapping, step 1. Let me use the red marker. Just recapping, students. Step 1, again, propose the statement. All right, that is step 1. You propose the statement. All right, step 2, prove that the statement is true for n equal to. Prove that statement is true for n equal to 1. That's steps 2. Step 3, assume that the statement is true for n equal to k. And then, last but not least, step 4, you are then going to test the hypothesis. Test the hypothesis that the statement is true for n equal to k plus 1. Test the hypothesis that the statement is true for n equal to k plus 1. And then we have step 5, although sometimes some people merge step 4 and 5, conclusion. And that would be it for principle of mathematical induction. I hope you have learned. I hope you can go back through the video. I hope you can then use this as a means to see if you can understand what your teacher was saying earlier and get some practice done. Have a good day, students.